So let's look at some unexpected results from these drawings. If we're following our rules for CO3, then we know that there needs to be 24 total electrons. We're going to put carbon in the middle, 3 evenly placed oxygens on the outside, use 2, 4, 6, brings us down to 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. So if we get down to 0, we know the rule is that one of the outside atoms is going to have to help out the one in the middle because carbon has not met the octet rule. Since all 3 of them are oxygen, it doesn't matter which one we pick. We can pick this one. We turn a lone pair into a double bond, and then we finish it. It is charged, so we put brackets -2. Here's the thing. How did I know which oxygen to pick? Couldn't it have just as easily been this one or this one? So that is what is going to start this next concept, which is called resonance. In reality, this double bond is not just actually going to stay put on this one oxygen. Nature is all about balance. So right now we have an unbalanced molecule where this oxygen and this oxygen are connected with a single bond, but this oxygen gets to be connected with a double bond, which is making the bonds very unequal in energy. If they didn't have the same identity, this wouldn't matter. But because they're all oxygen, this is not the way nature likes to be. So what ends up happening is this double bond actually starts kind of flipping through the molecule and trading off. So for a nanosecond, this oxygen gets to have the double bond. For another nanosecond, that one's going to get to have the double bond, and then this one, and it just starts rotating clockwise. And if we take a snapshot of carbonate at any moment in time, it could just as easily look like this, or like this, or like this. This is what we call resonance. It means that there is a bond that changes position in a constant way. So it's just constantly rotating through the whole molecule, which means that all 3 of these pictures are wrong and all 3 of them are right. The reality is that all 3 of them exist at the same time. Ozone is another example of this. So ozone is a weird molecule because 1 O is in the middle and 2 are on the outside. We use 4 to connect them. We have 14 left. 2, 4, 6, 8, 10, 12. Okay, so we know the rule is leftovers become a lone pair. But then also, once we've used our lone pair and gotten down to 0, the one in the center still does not have the octet rule met. So that means one of these outside oxygens is going to have to donate a lone pair. And again, we have the same situation where the 2 atoms on the outside are exactly the same. So why would this oxygen get to have the double bond instead of this one? We know now that in reality, this double bond is constantly flip-flopping back and forth between the 2. So ozone is actually made of 2 resonance structures that are equal, and one of them has the double bond on the left, the other one has the double bond on the right, and it's just constantly rotating between the 2. So how do you know if you should use a resonance structure or not? We're going to use a concept called formal charge, which is basically making sure that the element's electrons all got used. So in order to calculate the formal charge of an element, we're going to subtract how many valence electrons it started with from how many lone pairs are on it, and then 1 electron from each bond. We want 0. We want all the atoms to have a charge of 0. If they can't be 0, they should be negative, and the negative should be on the most electronegative element. So before we knew about formal charge, if we were drawing sulfur dioxide, we would have added up 18 electrons, we would have used 4, we would have had 14 left over, 2, 4, 6, 8, 10, 12, 14. And that means that we're going to need to turn one of these lone pairs into a double bond. So before we knew about formal charge, we would have looked at this structure and we would have been like, oh my gosh, look, a resonance structure. There's 2 oxygens, one has a double bond, one doesn't. So that means that this is going to go back and forth between looking like this and looking like this. But actually, that is incorrect. If we assign a formal charge value to one of these resonance structures, sulfur started with 6, that has 2 electrons of its own right here, and it has 3 electrons used up in each of its 3 bonds, which gives it a formal charge of +1, which is very unstable. Positive formal charges are no bueno. This oxygen over here started with 6 also. It has 6 of its own electrons, and it has 1 in a bond, which means that it has a -1 formal charge. Not too bad. This oxygen on the right has 6, -4, -2, which gives it a formal charge of 0. Amazing. So we have one really stable atom, we have one that's okay, and we have one very unstable atom. And if the one in the center is unstable, that's pretty much worst case scenario. So what we're going to do is use what we know about formal charge to make a judgment call. We already know that sulfur can break the octet rule. So the change that we made here, where we took a lone pair from this oxygen and turned it into a double bond, that was just to get to the octet rule. But we know that sulfur can break the octet rule because it's in the 3rd period on the periodic table, which means that it has d orbitals available. So if I come over here and I realize, all right, I need sulfur to gain 1 more electron and I need oxygen to lose an electron, then by turning another lone pair into another double bond, we now have reduced this to 0 and we have increased this one to 0. I guess I should have said that the other way. We increase this one to 0 and reduce this one to 0, whatever. So sulfur had 6. It used 4 in bonds and it had 2 on its own. So now, So now it has a formal charge of 0, making it very stable. This oxygen had 6, 4 electrons of its own, 2 in a bond. It is now also 0. So sulfur dioxide actually does not have resonance structures. So this model that we drew before, this would actually be incorrect, because using formal charge to check, we know that 2 double bonds and 1 lone pair is more stable than 1 single bond and 1 double bond. So let's use everything that we've learned to figure out what the best possible scenario is for this polyatomic ion. So C is the central atom, S goes on one side, N goes on the other side. We know that we need to use at least 4 of those electrons to make bonds, and then that gives us 12 left over. 2, 4, 6, 8, 10, 12. Okay. When we get to 0, we need to make sure the one in the middle is stable. It is not. So we have a couple of choices. Because S and N are not the same element, okay, we can take 2 lone pairs and do a triple bond on this side and leave a single bond on the other side. Okay, we could return that back to normal and do the exact same thing I just said to this side and make a triple bond like that. Okay, or we could do 1 from each. So we have a couple of options. So step 1, draw all the resonance structures. These are all the possibilities if we follow the octet rule. Oops, I'm missing a dot. Oops. These are all the possibilities using the octet rule. We need to use formal charge to figure out which one of these is the most stable. In our first example, sulfur started with 6, we subtract the 4 and we subtract 2 to get 0. Carbon started with 4, we subtract the 4 from the bonds to get 0. Nitrogen started with 5, we subtract 4 and 2 to get -1. So, following the same rules, the second set with the triple bond on sulfur gives us a formal charge of +1 on sulfur, it gives us a 0 on carbon and a -2 on nitrogen. And then our very last one, we have the -1 on sulfur, the 0 on carbon, and the 0 on nitrogen. So the most important thing is the one in the middle has a formal charge of 0, which in all 3 cases it does. So that means we need to rely on rule number 2, if I go back to remind you, which is that leftover charges should be negative and on the most electronegative element. So if we go back, we can compare sulfur to nitrogen. nitrogen is more electronegative than sulfur. So that means if we have an element without a formal charge of 0, it needs to be negative, and it needs to be on the one that is the most electronegative. So this one I'm pretty much for sure is out because the sulfur is +1. So we have to choose sulfur -1 or nitrogen -1, which is the best case scenario? This one. So the most stable version of thiocyanate is a double bond between both.